Extreme values on intervals. Let's begin by recalling the extreme value theorem, which we've already encountered on a couple of occasions. Suppose that f is continuous on a closed bounded interval AB. Then there exist numbers c and d in AB such that f of x is between f of c and f of d for all x in AB. Let's think about what this says for the function whose graph is shown here. Notice that the function has a least value corresponding to the lowest point on the curve, and that value occurs at a number c inside the interval AB. The value f of c here is the absolute or global minimum value of f on the interval AB. Also notice that there's a function value corresponding to the highest point on the curve that occurs at a number d in the interval. The value f of d is the absolute or global maximum value of the function on the interval. This theorem is often stated as follows. A continuous function on a closed bounded interval attains a minimum and a maximum value. We can also say, moreover, that if either c or d is in the open interval AB, that is the interior of the closed interval, then it is a critical number of f. For the function graphed here, notice that the function has a minimum value at a critical number inside the interval, and its maximum value occurs at the endpoint B. In this picture, again, we have a minimum value occurring at a critical point inside the interval, and here the maximum value is the value of the function at A. For the function whose graph is shown here, the minimum value occurs at the left endpoint, and the maximum value occurs at the right endpoint. Notice that there are two local minimum values inside the interval, as well as two local maximum values. However, none of those are absolute extreme values on the interval AB. Here's a procedure for finding the minimum and maximum of a continuous function on a closed bounded interval. First, find all the critical points in the interior of the interval. Then, compute the values of f at the critical points and at the endpoints of the interval. And finally, select the least and greatest of those computed values. For example, find the maximum and minimum values of f of x equals x plus 2 cosine x on the interval 0 to 2 pi. We'll first find the critical numbers. So we compute f prime of x. That's 1 minus 2 times sine x, which is equal to 0 when sine x equals a half. So our critical numbers are those values of x for which sine x equals 1/2, which are pi over 6 and 5 pi over 6. Notice that the function has many other critical numbers outside of our interval, but we're only concerned with those that are inside the interval. Now let's compute the values of the function at the critical numbers. F of pi over 6 is equal to pi over 6 plus 2 times the cosine of pi over 6, which is root 3 over 2. So f of pi over 6 is equal to pi over 6 plus the square root of 3, which is about 2.26. F of 5 pi over 6 is 5 pi over 6 plus 2 times the cosine of 5 pi over 6, which is negative root 3 over 2, and so we get 5 pi over 6 minus root 3, which is about 0.89. Next, we compute the values at the endpoints of our interval. F of 0 is 0 plus 2 times the cosine of 0, or 2. F of 2 pi is 2 pi plus 2 times the cosine of 2 pi, so we get 2 pi plus 2, which is about 8.28. So by comparing these values, we can now say that the minimum value of f on the interval 0 to 2 pi is the value at 5 pi over 6, which is 5 pi over 6 minus the square root of 3, and the maximum value is the value of f at the right endpoint 2 pi, which is 2 pi plus 2. Here's the graph of that function. Notice the minimum value occurring at 5 pi over 6, and the maximum value occurring at the endpoint 2 pi. Example: find the maximum and minimum values of f of x equals 4x cubed minus 8x squared plus 5x on the closed interval 0 to 1. We'll first calculate critical numbers. For that we need the derivative, which is 12x squared minus 16x plus 5. Fortunately, this factors into 2x minus 1 times 6x minus 5, and so we see that the critical numbers are 1/2 and 5/6. Now we compute the values at the critical numbers. F of 1/2 turns out to be 1. The value of f at 5/6, after a bit of arithmetic, turns out to be 25 over 27. Now we compute the values at the endpoints. F of 0 is 0. F of 1 is 4 minus 8 plus 5, which is 1. Therefore, the minimum value of 0, 1 is the least of those numbers, which is 0. And the maximum value is the greatest of those numbers, which is 1, and occurs at both 1/2 and at 1. Here's the graph of that function. Notice the minimum value occurring at the left endpoint, and notice that the maximum value occurs both at the right endpoint and at a critical number in the interior of the interval. One-sided derivatives at endpoints. Let f be defined on a closed bounded interval AB. The derivative of f at the left endpoint A is understood to be the right-sided limit as h approaches 0 of the difference quotient f of a plus h minus f of a divided by h. Notice that since a is the left endpoint, f of a plus h may be undefined when h is negative. Similarly, the derivative of f at x equals b, the right endpoint, is understood to be the left-sided limit as h approaches 0 of f of b plus h minus f of b over h. Or, equivalently, the limit as h goes to 0 from above of f of b minus f of b minus h over h. Essentially, what each of these does is define a one-sided slope at the endpoints a and b. For example, here, the derivative at the left endpoint is the slope of the line shown here, and the derivative at the right endpoint is the slope of the line that's tangent to the curve there. In this picture, at the left endpoint, notice that secant lines have positive slope that increases without bound, resulting in a derivative of plus infinity. And at the right endpoint, notice that secant line slopes are negative, approaching minus infinity, and so f prime of b here is minus infinity. Some remarks on endpoint extrema. Suppose that f is continuous on the closed interval AB, and that f prime of a exists as a real number or as minus infinity or plus infinity. If f of a is the maximum value of f on AB, then f prime of a is less than or equal to 0, or else f prime of a equals minus infinity. Here's a picture that illustrates this. Notice that the value at the left endpoint is the maximum value of the function on the interval, and the slope of the tangent line there is negative. Here's another picture to illustrate this. The left endpoint value is again the maximum value on the interval, and here the value of the derivative at the left endpoint is minus infinity. If f of a is the minimum value of f on AB, then f prime of a is greater than or equal to 0, or f prime of a equals plus infinity. In this picture, the minimum value occurs at the left endpoint, and here f prime of a is equal to 0. In this picture, the left endpoint value is again the minimum, and the derivative there is plus infinity. Suppose that f is continuous on AB and that f prime of b exists as a real number or as minus infinity or plus infinity. If f of b is the maximum value of f on AB, then f prime of b is greater than or equal to 0, or f prime of b is plus infinity. In this picture, we have a maximum value occurring at the right endpoint. Notice that the slope there is positive. Here, the maximum value again occurs at the right endpoint. The derivative there is plus infinity. If f of b is the minimum value of f on AB, then f prime of b must be less than or equal to 0, or else f prime of b equals minus infinity. Here's a picture where the minimum is attained at the right endpoint. Notice that the derivative there is negative. And here's a picture where, again, the derivative is attained at the right endpoint, and here f prime of b equals minus infinity. The role of the second derivative. Suppose that f is continuous on the closed interval AB, and that f double prime of x exists for all x in the interior of the interval. If f double prime of x is less than or equal to 0 for all x in the open interval AB, then the minimum value of f on the closed interval AB is either f of a or f of b. That is, the minimum must occur at one of the endpoints. If in addition f has a critical number c in the open interval AB, then f of c is the maximum value of f on AB. Here's a picture to illustrate this. Notice the graph is always concave down. The minimum value occurs at the right endpoint. Also, there happens to be a critical number inside the interval where the maximum value occurs. Here, the graph is concave down over the entire interval again. The minimum value occurs at the right endpoint, but there is no critical number in the interior of the interval. In fact, the maximum value occurs at the other endpoint. Here's another picture. Graph is concave down over the entire interval, and the minimum value occurs at the left endpoint. On the other hand, if f double prime of x is greater than or equal to 0 for all x between a and b, then the maximum value of f on the closed interval AB is either f of a or f of b. If, in addition, f has a critical number c in the open interval AB, then f of c is the minimum value of f on AB. Here's a picture where f double prime of x is greater than or equal to 0 over the entire interval. The maximum value occurs at the right endpoint. F does not have a critical number in the open interval, and so the minimum value does not occur in the interior of the interval. In fact, it occurs at the left endpoint. Here's another picture where f double prime of x is greater than or equal to 0 over the whole open interval AB. The maximum value of f occurs at the left endpoint. Here there is a critical number in the interior of the interval, and that's where the minimum value occurs. And here's another picture where f double prime of x is greater than or equal to 0 over the entire open interval. Notice that the maximum value occurs at both of the endpoints. There's a critical number in the interior where the minimum value occurs. We'll now state a theorem that turns out to be very useful for finding extreme values on open intervals. Let I be an open interval, and suppose that f double prime of x exists for all x in I. If f double prime of x is greater than or equal to 0 for all x in I, and if there's a number c in I where f prime of c equals 0, then f of c is the global minimum value of f on I. If f double prime of x is less than or equal to 0 for all x in I, and if there's a number c in I where f prime of c equals 0, then f of c is the global maximum value of f on I. Example: find the minimum value of f of x equals x cubed plus 1 over x on the interval from 0 to infinity. Let's first rewrite f of x as x squared plus x to the minus 1 power, so it will be simpler to take the derivative of f. F prime of x is now 2x minus x to the minus 2 power, and f double prime of x is 2 plus 2 times x to the minus 3 power. Now let's notice that f double prime of x is greater than 0 for all x in the interval from 0 to infinity. Therefore, if f has a critical number in that interval, its global minimum must occur there. So let's look for the critical numbers. Let's rewrite f prime of x as 2x cubed minus 1 over x squared, making it easy to see that f prime of x is equal to 0 when x is equal to the cube root of 1/2. Therefore, the minimum value of our function on our interval 0 to infinity is f of the cube root of 1/2, which is 1/2 plus 1 over the cube root of 1/2, or 3 times the cube root of 2 over 2. Now let's have a look at the graph of the function. Here it is. Notice the minimum value occurring at 1 over the cube root of 2. Another example. Let's find the maximum value of f of x equals 2/3 x minus secant x on the interval from minus pi over 2 to pi over 2. We'll take the derivative first. It's 2/3 minus the derivative of secant x, which we recall is secant x times tangent x. Now let's take the second derivative. Using the product rule, we first take the derivative of minus secant x, which is minus secant x tangent x, and multiply by the other factor, tangent x, and then add minus secant x times the derivative of tangent x, which we recall is secant squared x. We can now factor minus secant x from each term and observe that the other factor is tangent squared x plus secant squared x. Now, since secant x is positive when x is between minus pi over 2 and pi over 2, we conclude that f double prime of x is less than 0 on the interval from minus pi over 2 to pi over 2. Therefore, if f has a critical number in that interval, the value there must be the maximum value of the function on the interval. So let's look for critical numbers in our interval. A critical number will be a value of x where secant x times tangent x is equal to 2/3, making the first derivative equal 0. And let's rewrite secant x tangent x as sine x divided by cosine squared x. Now, we can rewrite 2/3 as 1/2 divided by 3/4. We know that sine x is equal to 1/2 when x is pi over 6, and cosine of pi over 6 is root 3 over 2, so sine x over cosine squared x will be 2/3 when x is equal to pi over 6. That's our critical number in the interval minus pi over 2 to pi over 2. So the maximum value of the function on that interval is f of pi over 6, which is 2/3 of pi over 6, or pi over 9, minus the secant of pi over 6, which is 1 over the cosine of pi over 6, or 2 divided by square root of 3. Here's the graph of our function. The maximum value occurs at pi over 6, and that value is pi over 9 minus 2 over root 3.